All right. So we're going to start lecture 3, talking about continuing our discussion of renormalized perturbation theory that we started. And I'm going to, because we didn't do loop calculations of QED, I'll have one extra lecture after this on Thursday on renormalized QED. All right. So a review of the previous lecture. If there are any questions at any point that come up, please do ask. We talked about the scaling symmetry, x mu going to lambda x mu as a classical transformation. This sits next to Poincare group and enlarging it to a set of space-time transformation. It doesn't have to be a symmetry for all theories. Some theories are scaling variant. And then we talked about next to scaling, there's another transformation, which is special conformal transformation, right? Special conformal transformations could be viewed as, this is, in my opinion, the simplest way to view it, as inversion, translation, inversion back, right? And inversion is a Z2 operation. All right. Conformal group in RD minus 1, 1 is SOD, 2. And in RD is SOD plus 1, 1. So Euclidean conformal group is Lorentzian Minkowski Lorentzian Lorentz group, Lorentzian Lorentz group in 2 higher dimensions, right? It's the Lorentz group, not Lorentzian Lorentz group. Lorentz group in 2 higher dimensions. All right. The generators, the nodal charges, classically are P mu and M mu nu. For the Poincare charges, and for dilatations are D and K mu. D is the generator of scaling, and special conformal transformation, the generator is K mu. Right? Okay, conservation laws. We talked about the stress tensor in the case of Poincare symmetry to be the current associated with Poincare transformations. Poincare symmetry here is again the stress tensor. So the conservation law for the Poincare symmetry, where del alpha mu is equal to 0, right? That's the conservation of stress tensor. Then for scaling, it's the fact that stress tensor is traceless. Now, if you have a relativistic stress tensor, it has to be symmetric. As the symmetric condition and traceless condition together imply that special conformal transformations hold as symmetries, right? The example of a conformal field theory you should have in mind are massless free fields, scalar or not, whatnot, right? So massless free fields are conformal field theories. For example, massless scalar is a conformal field theory, and phi 0 under a dilatation transforms this way, right, as an operator. And this d minus 1, 2 over 2 is the superficial dimension counting dimension, which in this case, the theory is so simple that you don't need to worry about anything. It's actually truly a quantum symmetry as well. All right, questions so far? This is called scaling dimension, by the way, of the operator. We talked about the renormalized perturbation theory. Renormalized perturbation theory, the starting point was that we said there is a renormalized field phi naught. We're going to there's a bare field phi naught. We're going to introduce a renormalized field phi r, which is related to phi naught by some factor called z half to be identified. And this z, we refer to it as wave function renormalization for the scalar field phi. For every field in your action, you'll have to have a corresponding z parameter. Good? So then what do? You start with the Lagrangian with bare couplings and bare fields. You write it in terms of a Lagrangian with the renormalized coupling and renormalized fields, plus whatever is the difference between the two. We call it counter terms. And then we're going to be doing Feynman diagrams. And in terms of the renormalized fields, treating counter terms as interaction, vertices and various interactions in path integral and Feynman diagrams. An explicit example is phi 4 theory. You start with the action, which is del mu phi 0 squared, right? I did this notation, I think. Is this, right? Minus plus. Lambda naught over 4, phi naught 4. This is your bare Lagrangian density, right? And then the minus signs are different from whatever. So I'm taking a minus outside of all the Lagrangian density. First thing is that your phi naught is z half phi r, right? So that's the first round. I'm just rewriting the first term. Then phi naught again for m naught squared is z phi r squared. And then this will have z2. All I've done is just rewritten it in this new variables. Then I take this and split it into two terms. It's the same expression, right? I write it as half del mu phi r blah, 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 blah. And whatever is the difference, I call it this way. These are the counter terms. And what's the difference? These coefficients are, of course, fixed in terms of z and the relation between m naught and mr and lambda 0 and lambda r. Good? Now, you want to do perturbation theory using this action, right? So from the point of view of this action, there is a diagram for propagator of phi r, which is mr, right? I over p squared minus mr squared. The pole of the propagator is mr squared. And also, now this new term, right, will give you a counter term, delta m. And the delta z part comes from this term, right? This term. The p squared of it comes from del mu squared, right? And then similarly for phi 4, you have the interaction minus I lambda r, and for the counter term for the interaction, you have minus I delta of lambda, right? So 3 counter terms here: delta of z, delta of m, delta of r. Good. There will be a delta of z for basically every Feynman diagram you have is going to acquire a counter term example, corresponding counter term. All right, so what's the renormalization condition? The renormalization condition is this. So you want to renormalize your theory at a certain scale, right? Which means that you're going to do calculations with this action, right? And you're going to find a propagator at 1 loop, 2 loops, whatever it is. You're going to calculate it and write it in terms of phi r. The result will be an expression which has these deltas in it, these counter terms in it. Now you're going to perform your measurement and read off the value of the mass, right? You equate the left-hand side with the right-hand side. You're going to do an experiment of this time for the propagator and for the vertex. This data coming from experiment will fix your deltas at that energy scale where you perform measurements. That renormalizes your theory. Now that you fix the values of delta, you go and calculate whatever diagram, right? Because this establishes a dictionary between their variables and the physical variables, right? So, for example, the propagator for phi r is going to be I over p squared minus mr squared plus terms regular at p squared equal mr squared, right? Because we said that almost by definition, the pole of the propagator is the physical mass, right? Now, to have this condition, it's not just the pole. It's actually two conditions. One is the pole, the other one is the residue, right? So the residue is going to fix the overall wave function normalization. So at 1 loop, this diagram, we're going to look at 1 pi. I didn't define 1 pi, did I? I'll define it later today. 1 pi diagram, so that let's not worry about what it means for now. Is the 1 loop diagram we calculated was this, right? At 1 loop, this was the only diagram that we had, and this is the counter term associated with it, right? Now, we write down this expression. This diverges. We're going to regulate it. Then this will be some answer. The 2 should be equal to this side. Good? So the 2-point function, I think maybe I should explain this first. All right. So we're going to see that the 2-point function is going to be taking the following form: I over p squared minus mr squared minus something to calculate, and that thing is going to be a 1pi diagram that we're going to explain. But importantly, the renormalization conditions would be that at the physical mass, this should be 0, right? So that the propagator at the physical mass is indeed what you observe is mr squared, and then the residue should be 0, should be 1 as well. This is a condition for the residue. When you take derivative with respect to p squared, right, that should not change this. What does this tell you immediately? It tells you that you're going to see this. You renormalize at a certain energy scale, right? But that is a particular value of p squared. Good. Now, as you change the values of p squared, you look at lower energies, right? Your mass is going to get corrections, right? We're going to see this. All of these are going to become clear. So at one loop, for example, here's what's going to happen. At one loop, this mp squared, right, which is the sum of these two diagrams, is going to be the following. It will be the counter term, which is I delta zp squared minus delta m. That was just by definition, and it was in the Feynman diagrams, right? And then there's this guy. What is this? It's minus I lambda of r over 2 integral of d4 of d dk d2 pi d I over k squared minus mr squared plus I epsilon. Is this part clear? Is this calculation clear? I'm using this renormalized perturbation theory, right, to calculate these two diagrams. Where does this factor of half come from? Where does this come from? What is this? It's a loop. It's just k that runs in the loop, right? This is a propagator in the loop, and you're integrating over it because it's a loop, right? Now, this factor of half comes from the Z2 symmetry of the diagram, right? And there's a vertex, just Feynman diagrams, right? Now, this at this at p squared equal mr squared, right, should become 0. That was the first condition. This is the first condition. The only p dependence is in here, right? So if this expression is to become 0 when p squared is equal to mr squared, delta z has to be 0, right? Because this term is p independent. Good. Now, to fix the delta m, you look at, oh, sorry, what did I say? This is what, this is the second part of what I said, right? The fact that dp squared of this, because it's p independent, dp squared is only from this part, right? So when you take dp squared, only this term survives, and the fact that this should be 0, it tells you that delta z has to be 0. Good. Now, the fact that p squared equal mr squared, this should be 0. This term you already throw out. Throughout, this is what you have, right? Now, this should be equal, the value of this should be equal to delta m. Good? But you have a little bit of a problem. The value of this is diverges. Counter terms are divergent, their values. What are we going to do? What we're going to do is we're going to regulate it. Pick a regulator, renormalize your theory with the regulator, right? That establishes a finite dictionary between observed stuff and the bare variables. Now you do the calculation with this regulator for all your other diagrams. You use a dictionary. After you use the dictionary, you can take the regulator away, right? This is hiding infinities under the carpet, but we're going to make sense of it. Does it make sense? To establish a dictionary, you have to regulate. So you can write down explicit expressions for these delta z's, delta m's, and stuff. right? But once you regulate it, you do a calculation and all sorts of different higher loop calculations, right? Or no, it doesn't have to be higher loop. Your other calculation, right? Now, it will depend on the regulator, but if you recall, then you take the regulator away and everything will remain finite. Recall what we were talking about renormalization last semester. Renormalization, the principle of it was that deep in the infrared, at low energies, the physics is independent of the UV details. Whatever we're doing to this regulator is deep in the UV. Something is divergent, right? Regulator says, let's just modify the UV in some ad hoc way, right? To just make this converge. Now, the principle of renormalization is behind it. It says that, well, because the UV doesn't matter for the infrared calculation, this is okay, right? So you regulate it, you subtract that. It's sort of like saying this. There's a quantum field theory has arbitrary short wavelength physics modes. A sharp cutoff in momentum, which is one way of saying, one way of imposing a regulator, says that arbitrary high energies, the modes are so heavy they do not propagate. Right? That's what the cutoff says. It says that the corresponding mass to those modes is infinite. So they don't propagate. Right? When they don't propagate, that's a way of regulating it. Now, why is your calculation correct when you regulate and calculate the low energy things and tweak the regular way? Because of the principle of renormalization. It says that low energy physics is independent of the UV. And this regulator, you do at very, very high energies. You could take it to be arbitrarily high because this divergence has to do with arbitrary short wavelength, right? It's sort of saying that in LHC we're doing an experiment, and we're going to pick the regulator to be Planck energies we've never observed, and we believe the details of those energies shouldn't matter for LHC, right? Okay. Now, one thing that I haven't told you is that, and we're going to see today, is how to regulate this to get this answer. All right? We're going to do that. So how did we calculate this integral? I'm going to go through it for the case of a scalar field, and then we're going to repeat this over and over again. Are there any questions about the general principle of perturbative renormalization? So we said renormalized perturbation theory, you start with a bare action, you find these renormalized things. You treat the counter terms. You write down the bare action in terms of these renormalized stuff plus counter terms. You treat counter terms as like terms in the Feynman diagrams. Then you normalize your theory at a certain scale, which fixes your counter terms in terms of observed variables. Now you have renormalized it and run the machinery to do other calculations. A theory is renormalizable if the number of renormalization conditions is finite. Right? That makes sense. In this case, it's basically the propagator, right? You look at it's just renormalized MR, right? All right. So now here's a trick I'm gonna explain on how to deal with this interval that's divergent. It's basically the same principle. There are many ways of regulating this integral. One way we talked about before was a sharp momentum cutoff. You could do that in this case, but I don't want to do it. I want to use something else called dimensional regularization because it's more useful, meaning that dimensional regularization works in a larger set of theories than the sharp momentum cutoff for reasons that I'll explain later today. All right, so let's first see how it works. First observation, this is a Lorentzian integral, right? So this is in d+1 dimensional, it's in Lorentzian momenta. First step to do this integral is to do a Wick rotation. So you treat it as Euclidean. Right? Is that clear? That the first step is clear? All right. When you treat this as Euclidean, K Euclidean, and so what is it? It's Wick rotation. It sends T to I T Euclidean, right? Now, what was K0? Of course, the vector part of K doesn't change. K0 is what? Energy. It's the conjugate variable to time. That tells you that Euclidean K, right, will have a zero component, which is different from K0 by an I, or minus I. Good? Now, after Euclidean continuation, what you're going to have is 1 over Ke squared plus 2m squared, dd of K, 2 pi of D. We are in 4 dimensions. So now the second step is generalization to D space-time dimensions. Let me explain this. So there's only 2 steps, right? But I want to make sure that, yeah. Clear. What we should be calculating is this and I'm not going to put these. These are Euclidean. This diverges. This diverges. But we notice that the divergence occurs when this power is 4 exactly. Right? Why is that? Naive dimension counting. At deep in the UV, this m squared is irrelevant. This goes like 1 over K squared. This is 4 powers of K. Right? So by dimension counting, this blows up like lambda squared, the cutoff squared. We notice that if I just put some arbitrary D dimensions, right? For the right values of D, this and D here as well. For other values of D, low enough values of D, this actual integral is regulated. In fact, we know the answer for this. We're going to see that. So in terms of D, 4 is here, right? 3 is here. It's divergent, divergent, right? And then low values of it are not divergent. It turns out that you could make sense of this integral for complex values of D. Doesn't have to be integer. Another way of saying is this: you evaluate it for low values of D, and then you analytically continue. That's what you're doing. Good. So before doing that, you notice you did something funky. Can anyone tell me what happens the moment you just change the power? This is called dimensional regularization. You change 4. You change the naive space-time dimension. What happens? The first thing that happens. Of course, you change the dimensionality of the whole thing. So if this is supposed to be something physical, this has the wrong dimensionality. You have to introduce, so there's lambda over 2, right? There's lambda over 2. You have to introduce a dimension-full parameter, mu, some mass scale, right? To the right power, which in this case is mu to the power of 4 minus d. So that is correct dimensional. By dimensional analysis, correct. Right? This is simple. This is called dimensional regularization. And it's sort of like, the sharp momentum cutoff would have been something like this. This is sharp momentum cutoff. Sharp momentum cutoff requires a scale. You have to introduce a scale. Here, also, there's no free lunch. You have to introduce a scale, right? But the scale comes in very different. Good? Is it clear? This is called dimensional regularization. So now that you introduce this, you can perform this integral, and you're going to see it's going to be given in terms of gamma functions. Gamma functions famously have a bunch of poles for integer negative values, and d equal 4 is going to be one of those points. Good? But this is a regulator, so we're going to carry this power of d as a parameter in our calculation in our renormalized perturbation theory. We renormalize the theory with this d, Then we're going to calculate. This establishes a dictionary between physical and bare parameters that depend on mu and d. Right? Then we do another calculation in terms of mu and d. We use the dictionary. Sorry, it's going to be in terms of the bare parameters. Then, using the dictionary, we could relate everything to the physical variables. And at the end of the calculation, I take d to 4. This everything is gonna fall out, and it's gonna become finite. Good. All right. So now let's focus on how this integral is done. So in full generality, this is the answer. This is just like an answer. dd of k of 2 pi d. Work this out. Why? 1 over k squared plus delta to the power of n, dd of k of 2 pi d for, we'll take the following form. Delta to the power of d minus n, gamma function of n minus d over 2, gamma of n, 1 over 2 pi d over 2. When it converges. Right? Where in our case, n is equal to 1. So what do we find? We find lambda over 2, right? M squared over 4 pi to the power of d over 2, gamma of 1 over d over 2, m squared over mu squared, d over 2 minus 2. Why is that? Because delta, in this case, is m squared. So you end up with m squared to the power of d over 2 minus 1. Right? There's one power right here, and then d over 2 minus 2 here. That's all of it. And then what you have outside is mu to the power of 4 minus d. Right? That is mu squared to the power of 2 minus d over 2. So I packaged it this way. Notice that as d goes to 4, this thing diverges because this gamma function diverges. That becomes gamma of minus 1. You know what gamma functions are, right? Like gamma function is an analytic continuation of like factorial. Good. So in the dimensionally regularized theory, this establishes your connection. So in the dimensional regularized theory, lambda 0 is 0. The counter term for z is 0. Counter terms for m is this. Good. This is it. You're not going to take d goes to 4, because if you do, it blows up. This is already regulated. It has been dimensionally regulated. This dimensional regularization. Good. You make your integrals divergent or converge by treating space-time dimension as some analytic parameter.
Where did mu go?
Very good. So when you did the integral here, okay, good. Mu goes to the following place. So yeah, I did not explain that. This is the answer to your integral, right? To fix delta m, you will have to evaluate. You have to write these two conditions at some p squared, right? Mu squared, you have to tune it to mr squared. Mu squared, you tune it to mr squared. That's what you do. We're going to see more examples of this. Another way of saying it is the following. Another way of saying it is that let's look at the dimensionality of delta m. Right? What is the dimensionality of delta m? It's mr squared 2, mr squared 2 d minus 2 over 2, This means that these are all dimensionless, right? Lambda of r is dimensionless, right? This means that this has dimensionality of mr to the power of d, right? Mr to the power of d, because this minus 2 and this, sorry, d over 2 minus 1. Good? That's the dimensionality of it. Now, where does this delta m sit? Delta m is evaluating the value of this diagram, right? This diagram is added to lambda of r. So you better have the same dimensionality. The dimensionality is off precisely compensated. The off dimensionality is compensated by mu squared, right? Good. All right. So location of the pole is this condition. Residue of the pole is this condition. The divergence is regulated by dim reg, dimensional regularization. I call it dim reg. Everybody does. At the cost of introducing a scale mu. Renormalization scale is set by the energy scale of the internal legs. Right? P squared equal mr squared. Bare couplings are independent of mu. This is important. Of course, bare couplings are independent. Right? So delta of z is this, and delta of m is this. All right. So that was for the renormalization. We just looked at the renormalization of the propagator. Now, for the vertex, you're going to have a similar condition. The amputated vertex for renormalized 4 phi r's has to be minus I lambda of renormalized. At what energy scale? Now, this depends on Mandelstam variables. We're going to evaluate this at S equal 4 mr squared. At that value, it has to be minus I lambda r. Do you guys remember the physics of the Mandelstam variables? Should I review it? This was towards the end of the semester last time. Consider 2 to 2 scattering. Okay? In 2 to 2 scattering, with the signature which is minus 1 plus 1 plus 1 plus 1 plus 1, S, there are 3 variables, S, T, and U. Okay? S is minus K plus P squared. Maybe I write it P plus K. That's better. Minus. Why minus? Because of the signature. Because you want S to be positive. Right? That's why I wrote the signature. Now, what's the interpretation of this? Center mass energy. Why? Because if you look at the center mass for this collision, the P part of the vector part of P and the vector part of K have to be minus of each other, right? So this guy will be basically P0 squared plus K0 squared with minus signs overall, and the minus signs cancel with this. So this is center of mass energy squared. Good. Now, what is T? T is the momentum transfer. It's K prime minus K squared. This is negative in this convention. What is important is that if you switch the convention of this to plus, minus, minus, this is going to become positive. This is going to become negative, become positive. The relative sign of them, the physical the physical range of variables always has a relative sign difference between the two. So that's, in this notation, this is positive and this is negative. Right, and then this is minus p prime minus k squared. The center of mass has this advantage that when you do the collision at the center of mass, this gives us this interpretation, right? Now, the final beams come out like this, right? There is a scattering angle, theta. Actually, no, I don't want to. Theta is defined this way. Theta is defined. So if these are going in, right, and then this guy is this. This is theta. How much is deflected? If there was no interaction, this would just pass through. It's deflected by some angle theta, and then this comes out. Good. T and S are related by this cosine and sine thetas. I'm not going to repeat that statement, but basically, in the limit that masses are very small, so if masses are very, very small, just keep this in mind. T is minus S1 minus cosine of theta over 2, and U is minus of S1 plus cosine of theta over 2. When the masses are small. The theta equals 0 is called forward scattering limit, right? Because basically there's no deflection. Anyway, so these are Mandelstam variables. T equals 0 equals U equals 0 is theta equals 0. Now, at one loop, what is this amputated diagram? This is there's a vertex at the 2 level, and there are 3 diagrams like this, and you have to add the counter term for the vertex. Good. Should I add anything else? Why am I not adding? This. Think about that. Why am I not? I'm not actually good answer it right now. Why am I not adding this? You're thinking on the right. You're on the right track. This is higher order. How do I know that? I know it because see what was the value of this? This was used to cancel the divergences in this. So the divergences in the one loop diagram was used to cancel this. So this carries like the vertex lambda coupling. So this is higher order. Good. So at this order, this is all I need to add. So we're gonna use the dim rig to renormalize this at some center of mass S equal 4mr squared. Why 4mr squared? What is S? Yeah, it's the on shell value, right? But it's the on shell value where, so okay, no, it's not just the on shell value. So what is S? Is E1 squared plus E of K squared plus E of P squared. Like energy of the first one plus the energy of the second one, right? What is, this is a relativistic theory. What is this? This is M renormalized squared plus momentum 1 squared, right? No, sorry, I said it wrong. This is the center of mass energy. Yeah, so it's 2e squared. Sorry, 2e squared. Right? Now, let's say they have the same mass, right? So this is 4 mr squared plus k squared. Good? This is the rest mass. If it has momentum, the energy of it is going to be like this. Right? So the renormalization condition, when you put it at 4 mr squared, you're taking a limit where these particles are colliding very, very slowly. Good. All right, so this is all I wanted to. So here, up to here, we just went through. Structurally, we described how renormalized perturbation theory works. We're gonna see it in action in detail, in more detail in QED. Okay. So here it is: quantum electrodynamics. It's a theory when you have a Dirac fermion coupled to a U1 gauge field. Here's the action. This is a fermion psi, and you have the action for the photon, right? Which is just a U1 gauge field. It's just a propagator, right? There are no interactions. And then you have a coupling between the photon and the fermion. What are the Feynman diagram? What's the Feynman diagram content of it? It's the propagator for the photon, right? Mu nu. What was this? This is that projector P mu nu to the transverse direction, right? K squared plus minus I epsilon. You remember what this was, right? This is just eta mu minus k mu over k squared. What does it do? It projects out the direction, the component of k mu that's in the direction of propagation. Another way of saying that is that k mu p mu nu is 0. This we massage into word identities, right? Good. So that's one. Then we have the propagator for the fermion. What was it? Well, we write it down. ISF, which was 1 over K slash minus M plus I epsilon, right? We wrote it this way, actually. We wrote it K slash plus M K squared minus M. Right? And then we had the vertex. What was the vertex? The value of it? 3 level? I.e. not gamma, right? All right. Then we did it as 3 level calculations. We talked about the scattering of EE, Compton scattering, and the scattering of electron, positron, all of that, right? At one loop, what are the diagrams we're dealing with? We talked about this last time. So what are all the one loop diagrams? There is the propagator at one loop will acquire correction. This. It's called vacuum polarization. The fermion propagator will acquire one loop correction. What is the diagram? Right? And then the vertex will acquire correction, which is, so this is the vertex correction at one loop, right? This is the fermion mass. And then this was the vacuum polarization. It was important that the vacuum polarization should not introduce mass for the photon, right? Why is that? It's unphysical. But how do you impose that? This was actually the content of the word identities, right? There should be no degree of freedom in the direction of propagation. All right. Okay. I said everything here. And the full propagator, one loop or not, right? The full propagator for the photon, call it delta mu nu. It better be the case that delta mu nu is a projection acting on some delta of q squared. It better be the case, right? Because this is just a projection. So we know the dependence on mu and mu. We know the tensorial dependence of it. Everything is fixed up to this delta of q squared. Good? All right. So now, oh, is this out of order? Oh, I think it's out of order. No, well, maybe I don't have a slide for it. Now, oh, no, I have it. Sorry. This is the Lagrangian density. You write down the Lagrangian density for A mu, for A0 bare and psi bare, right? Introduce psi renormalized. So between, you have to introduce renormalized variables, right? So previously we had phi naught was z half phi of r. Now we have two fields, right? We have A mu is A mu naught, bare A mu is A mu renormalized z2 to the power of half and psi mu psi 0 is z3 half psi renormalized. I have to introduce one for each of them. I'll tell you why I called them 2 and 3 in a second. Oh, sorry, I said it wrong. 2, 3. It's clear that this is supposed to be a 2-point function of the renormalized field. Therefore, there will be a z2 appearing here, right? And this is going to be a 2-point function of the photon, so there will be a z3 appearing here. Good. What about the interaction term? The interaction term had the coupling had bare E0 gamma mu, right? Now I put the renormalized guys, I pick up Z2, Z3 to the power of cube. Because the interaction has 2 copies of psi 0, that will give me Z2, and 1 copy of A mu, that gives me Z3 half. This we're going to interpret as a renormalization of the electric charge, right? So then we could write it, we could write it this way. So E of R is going to be Z2, Z3 half, E0, right? We're going to give this a name, Z1. That's why I call those Z2 and Z3, right? We're going to go through this in more detail next time, but all I want you to know is that now there are 2 guys, Z2 and Z3. And then every time there is renormalization of the charge, it's related to this particular combination we call Z1. All right. Now let's define what a 1pi diagram is. 1pi is one particle irreducible. These are diagrams that if you cut them anywhere, they will not become disjoint. One cut will not make them disjoint. Is this diagram 1pi? It's not. Because if you cut it here, it will not be disjoint. Or if you cut it anywhere else, it will not be disjoint. The ambiguity is what I'm talking about, right? Or for example, is say this diagram. Let's see. Is this diagram 1pi?
just the extent internally. Small one.
But does it become disjoint? What kind of cut? No, this is one pi. There's not a single cut. You're not allowed to cut the external legs, right? Internal legs. So what's an example of something that is not one pi? Any thoughts? Is this one pi? No, because it's an internal leg. If you cut it here, it becomes disjoint. So one pi diagrams or one particle reducible diagrams are those that by one cut could not become disjoint. Why do we? It turns out that it's a very helpful way of thinking about diagrams. In general, consider the propagator, full propagator, right? Full propagator will have one pi and not one pi diagrams. The point is that all the diagrams could be systematically written in terms of one pi. Why is that? Well, take the one pi diagram here, right, at one loop. Repeat it. This is not one pi, right? Now, take another one pi diagram. This is another one pi diagram. This is another one pi diagram. Good? So in general, you have a combination of all of these guys. Here's what happens. In full generality, for this guy, for the propagator, you could do it. You could write it this way: it's a free propagator from one pi plus one pi repeated twice, plus one pi repeated 3 times, plus one pi repeated 4 times, and this is a telescopic series. You could resum it and write it as 1 over 1 minus 1 pi. So all you need to calculate is the one pi diagrams. Is that step clear? Because by definition, a non-one pi diagram is, let's say, something that's two-particle reducible, right? It could, by one cut, there's one internal line that if you cut in half, it becomes one pi, right? That just means take one pi and paste it next to the other one. You're just successively applying it. So it's this diagram, and then the next one is this diagram, so on and so forth. The resummation will tell you that it becomes like this. Good? Now, to see how it works, think of the propagator, the first term. So it's I over Q squared eta mu null in Feynman gauge. Right? Then what is the 1 pi? We call 1 pi pi mu nu, right? And then there's a propagator here, there's a propagator here. Now you look at this guy, there is a propagator, 1 pi, propagator, 1 pi, propagator. Good? Now the 1 pi, we already figured out what the structure of the indices were. So everything is fixed up to this pi q squared. Right? So the full propagator could be written as minus I over q squared, this p mu q, over q squared, 1 minus pi of q squared, minus this expression. Can you see this? What can you work this out in your head? What is happening? Let me do it on the board. At least hint at what's going on. So the full propagator became 1 minus 1 pi, right? This is the amputated one, right? This is the amputated. Which now, what is this guy? This is pi mu nu, which is what? This is pi mu, which is 1 minus q mu over, oh sorry, not 1. eta mu, that projection, right, times pi of q. Good? This is all good. The step that you have to convince yourself of is that when you put the pu mu here, and that is equivalent to this. So there's pi of q squared. Of course, there's something wrong with what I wrote. Because I wrote 1 minus. That can't be 1 minus. This has mu indices. Right? So you have to repeat this carefully, as I was hinting at. You have to do this calculation carefully, and it resums to this expression. But the point is exactly that the only thing that matters is this pi q. The tensorial structure of it is fixed by word identities, by the fact that there should be no propagating degree of freedom in the direction of propagation. There should be no degree of freedom in the direction of propagation. Right? So it becomes the full propagator, once the dust settles, becomes just the regular propagator, right? Times 1 minus 1 pi. And then this is just that eta mu or something. Good? Now, what is the condition that there is no mass renormalization? Pq squared, as q squared goes to 0, should not be singular. Because this whole thing is sitting next to 1 over q squared. Right? If it becomes singular, your pole structure completely changes. The requirement that this expression, the full propagator, has poles at m equals 0, at q equals 0, requires that this is nice, non-singular at q going to 0. Your pole, the order of it, nothing should change. Good? So once you renormalize deep in the infrared, because how are we renormalizing the propagator for the propagator for boson? Sorry, for a scalar field. We're evaluating a 2-point function at the physical mass. What's the physical mass of a photon? 0. So when you renormalize it, the parameter that enters it is z3, which is 1 over 1 minus pi 0. Right? Because that is this is supposed to be a mu of renormalized. Each of them carries a z3 half. So this carries a z3. Z3 would be 1 over 1 minus pi 0 when it's renormalized. Good? So, in summary, in renormalization of the vacuum polarization, the mass cannot change. The only thing that can get renormalized is the wave function normalization, right? Just the residue. It's just the residue that's changing. For a propagating photon, the mass could change, and so could the wave function normalization. But we saw that at one loop, it happened to be the case that the wave function normalization of the scalar field here was 0. It just happened to be the case. If you go to higher orders, that's no longer true. Right? But here it's a principle. Doesn't matter what order in perturbation theory you are. It's a fully non-perturbative statement. Photon cannot acquire mass. Period. Good? Now, when I was writing these expressions, I said that there is a connection. Once you know the renormalization of A and renormalization of psi, you know something about renormalization charge, right? Because the renormalization charge had to do with Z3, Z2 half, right? One photon, right? And to see that, let's just elaborate on that a little bit more. consider the following diagram. I mean, what is the point of renormalization of charge? What's the point of the charge? It goes into the calculation, for example, scattering of electron, like Compton scattering, for scattering electron and photon, right? Or scattering electron positive. That's where it goes to. So consider the following process, right? There are E's, E naughts, and this propagator for the photon now has Z3 of Q squared, right? That you could view as some sort of a normalization of E's. But now something really, really interesting happens. Can you tell what is it? This photon in the middle, right? Doesn't have to be on shell, right? There's some incoming energy. Well, sorry, doesn't have to be, I misspoke. Q squared need not be zero for it. The Q squared need not be zero. So this renormalization is now Q dependent. Why? Because this propagates. What is Q? Q is the external legs, right? The energy of the external legs. Now this guy will have some amount of energy that propagates, right? Now, this is the very first place where we see that the renormalization of charge depends on the energy scale. As you scatter electrons, right? As you scatter electrons at different energies, the effective charge they feel depends on the energy at the scattering, center mass energy scattering. So for example, alpha zero, let's say you normalize your theory at some scale, right? That scale is very, very low energy. The scale of normalization, we wanted to get the right propagator at very, very low energy for the photon, right? That will give you alpha zero. What is alpha zero? This is a QED alpha, coupling of alpha QED. What is it? Sorry?
Alpha 1/37.
Yeah, 1/37. But what is it? It's E naught squared over 1/37 is already a normalized answer. It's E naught over 2 over 2 pi or 4 pi. Right? The alpha of QED is, if you recall from scattering, it was just E naught squared over. So the alpha at different scales are related by Z3 of Q squared. What happened? Let me summarize again what happened. We said, recall the idea of normal perturbation theory. You renormalize a certain scale. For example, we normalize the propagator photon at zero scale, zero energy, right? Because we wanted to write down the propagator at mr equal at q squared equal mr squared, right? And mr is zero, so we renormalize at q equals zero. But for once you normalize it, whatever diagram you're calculating, you have to write the propagator at 1 over q squared, blah, blah, blah. So it will have propagator will have q dependence. What enters in this calculation will have q dependence in explicit. This is the very first part of like a principle that we'll come over and we're going to discuss over and over again. So as I said, alpha naught is E naught squared over 4 pi. It's a bare coupling. It's the renormalized coupling is going to be related to it by just powers of Z3. All right. So now how are we doing time-wise? No, I should do this. So what am I gonna do in the remaining? Let me see. What is realistic? No, I can maybe. Well, let me keep pushing. So now consider this one PI diagram. We're going to calculate it, right? We're going to see what this pi is. Good. And you wouldn't be surprised that it involves a similar integral to the photon we just did and similar dim reg idea. That's what I'm gonna walk you through. So as one loop, this is the diagram that contributes. Good. The amputated one pi diagram at one loop is the following: -1. Okay, I have it here. Let's just zoom. -1 because there's a fermion loop. Minus IE. Oh, actually, very good. I'm gonna put a Q here for now, in anticipation of the fact that my fermion might have like electric charge, which is like 2 or 3 or 4 for generality, right? So because we're going to do this calculation, recycle this calculation much later for like a theory with a bunch of fermions and they have different charges, right? So this is the units of how many charges. So for electron, it would be 1, right? So minus IEQ squared. Those are coming from the vertices. Now, what is this? This is ISF K minus Q, this propagator, gamma nu, right? ISF K. Good. This is what we should have as pi mu nu, right? Because this is mu and this is nu. And we're going to calculate this. Now, what was SF? I erased it. SF is K slash plus M over K squared minus M squared, right? So here are the K squared over M squared, and the slash ones you expand, you get this expression. I've actually already simplified my life. There are gamma mu's here, and there will be a bunch of gammas and the slashes, right? I'm not dealing with them yet. Or you could think I've performed trace or something. Let's ignore that for a second. We're going to come back to that, right? So this is the structure of it. Because those are matrices. These are matrix elements of them are like this. All right. Let's see the divergent structure of this. This is one of, if you do a sharp momentum cutoff, let's say first, we do Wick rotation. So we're going to go to the Euclidean K. And we're going to do a sharp cutoff, momentum cutoff, in an energy cutoff in Euclidean space, lambda. This goes like lambda to the power 4, right? This goes to 1 over lambda squared, 1 over lambda squared. This goes like lambda squared. Good? Is that clear? Now, what matters is that this part you have to pay attention. This is order lambda squared. This is order lambda squared. And so is this order lambda squared. But we do know, whatever the hell this answer is, it better satisfy word identities. There should be no, all the tensorial structure of it has to be that projection times some pi of this. Good? Any part of this integral that is in the direction of propagation, right, would have the interpretation of mass or photon. Good? And it has to be discarded. It's going to be discarded by just gauging variance. One way of saying that is that, yeah, okay, well, let me just leave it that. Good? We'll be inconsistent with word identities. All right. Let's dimension regularize this. This diverges like, so this is lambda 2, lambda 4, lambda 4. This diverges like lambda squared. Naively, diverges like lambda squared. Good? In 4 dimensions. In 2 dimensions, diverges like lambda log lambda, and anything lower, it converges. Good? We're gonna, here are the set of words that we say. We're gonna, in dimension dim reg, we're gonna pretend the propagator is an analytic function complex dimension D with isolated poles at integer D. There are spinners. So what did we do? We said we're going to replace 4 by some power D. That looks like I'm doing my calculation in a different space-time dimension. What happens to my gamma mu and gamma nus? They were coming from representation theory of SO3, 1. What should I do with those? You have to be careful with those as well. So the simplest way to do it is to go back to Clifford algebra, which was the form of representation theory of spinners in arbitrary space-time dimension. What were the identities that hold? Well, Dirac algebra, right? Gamma mu is D plus 1 identity. In arbitrary dimensions, these hold. Gamma mu is 1 minus D gamma nu. And gamma matrices in arbitrary dimensions should be traceless. Oh, sorry. I misspoke. I just misspoke. The gamma of 2m plus 1 in odd dimension, gamma 5 is the gamma 5 that's traceless. Sorry, I misspoke. All right. That's how we deal with indices. Lorentz with Dirac's indices. There's only one thing that you need to be careful with. This trace of identity. It turns out that you could just take it to be some arbitrary function of D and it won't matter. Because we could always absorb it in the couplings. So maybe I should stop at this point. Actually, no, I'm going to say one more thing. So you already should have a sense of, before next lecture, when we're going to do the calculation, you should have a sense of what's going to be in the calculation. We're going to take those 3 diagrams. We're going to do dim reg, right? And then renormalize the theory. The dim reg would involve first weak rotation, then introducing, replacing the dimensionality of the integral by from 4 to some arbitrary dimension D, introducing a scale to compensate for that, and then renormalizing the theory. Good. Now, why am I doing dim reg and not sharp momentum cutoff? Any guesses?
You had this problem that anywhere near the cutoff,
right. So the principle, you're right. The main principle is this. I've said this before. We motivated that the UV behavior doesn't matter for infrared, so you could pick it arbitrarily. That's the point of a cutoff. But the UV physics doesn't matter as long as it doesn't violate important laws, right? If your theory has a symmetry, you're only allowed to pick whatever UV behavior you want that is consistent with the symmetry. Your regulator should not violate the symmetry transformations. Because then you're not guaranteed to recover your physics, right? The physical intuition is that the symmetry is exact in the Hilbert space, right? It's not an approximate notion. It holds at arbitrary scales, UV, infrared, it holds, like the whole thing has symmetry, right? But physically, the UV modes, the details of them, which also respect symmetry, should not matter. So you have to pick a renormalization scheme that is consistent with, a renormalization scheme or regularization that's consistent with symmetries. The problem, as we mentioned, with a sharp momentum cutoff is that it's inevitable that the photon will require mass. Now, that's awful. That's nonsense because we haven't said this much, but gauge transformations are not an actual symmetry. It's just a redundancy of the description. It's a lot worse than that, right? It's a lot. There's simply no degree of freedom in the direction of propagation of photon. If our regularization introduces one, we're hallucinating. We're talking about a different theory, right? Now, here is I just articulate the principle again. Whatever regularization you use in renormalization, it has to respect your symmetries. What if there exists no regulator? So why are we introducing regulator? Because to tame quantum effects, right? What if you have a classical symmetry that there exists no regulator that preserves it? That's called an anomaly. If you have a classical symmetry that there exists no regulator that could preserve it, there's no way of altering the UV physics, right, such that this is actually preserved as a full quantum symmetry. That's called an anomaly. We're going to come back to this later in this course. Now, gauge invariance is not a symmetry. It's just a redundancy of the description because we wanted to insist on local description of the action. Gauge transformation, gauge invariance cannot be anomalous. You simply cannot give mass to photon, period. So it must be anomaly free. I'll stop here. Any questions? Yeah.
Trying to think of this visual picking scales. If I'm trying to normalize we're saying this, so we typically like sounds like we typically renormalize at like a mass scale of that.
If you're normalizing the propagator, you do that. Right. Well, actually, for vertex also. Yeah. Go ahead. Yes.
Okay. So if I run any plus or minus collider at 100 GeV, which is right around the mass scale, this normalization scheme will describe that physics very well.
Right.
If I then run any plus or minus collider at a mass scale 10 times higher,
right,
does this calculation break down at that scale?
This is exactly where renormalization will come in. So here's what happens: you renormalize the theory at some scale, and then do a calculation at an arbitrary scale, right? So you normalize at some q equal to 0 at the infrared or something. Then you do the calculation whether you're shooting, colliding things at some arbitrary scale. Once you convert, you use your dictionary to transfer. You get an answer which is physically sensible. What happens is that the propagator you normalize at a certain scale is something, but at a different scale there is an effective different mass you could calculate, which is scale dependent. Quantum effects it's a running of mass. X actually increases.
Okay.
So you normalize because mass is a relevant parameter. So you normalize a certain scale, you fix it. You read the energy, the mass of this particle is this at this energy scale, right? And then what do? You are gonna do the calculations at lower energy scales, and you see the mass goes up. We're gonna see that. It's a relevant deformation as a coupling grows towards infrared. Yeah. Any other questions? Sorry, I went over time. No, thank you. But that's going to be all about RG. So that's exactly what we're going to discuss in RG.